hopefully.
Yep.
All right, thanks everybody. I'm very glad to be here to help kick this off this morning, and thanks to Abishai and Joel and all the organizers for inviting me to be here. It's my first time. Very excited to hear everything that's been going on. So I'm going to talk to you about a few papers that myself and my group have been working on, and I'll focus a lot on some work I've been doing over the past few months on reionization with a whole host of theorists from a few teams listed there at the bottom. So if we want to understand reionization, there are, of course, many, many things that we need to know, but when I think of it, at least from an observer and really from a galaxy point of view, there are sort of three critical quantities or three key items we need to know. The first one is, what is the UV luminosity density? These are the photons that we can observe, the non-ionizing UV photons. So for this, we need to measure the UV luminosity function, the distribution of galaxy luminosities, and we also need to integrate that function, and so we need to know actually how far down do galaxies actually form. We don't expect it to go all the way down to a single O star. It goes down to some limiting magnitude. So that's the first one. The second one is, of course, those aren't the photons doing the reionization. It's the ionizing photons. So we need to have some understanding of the stellar populations. How do we convert from the observed UV to the ionizing UV? And this is often parameterized by this parameter here, psi ion, called the Lyman continuum photon production efficiency. And lastly, and kind of the biggie, is how many of these photons actually escape the galaxy to be available to ionize gas between galaxies, or the intergalactic medium. And so we'll talk about these items. So the first one is sort of the easiest one because it's the one that many people, including many people in this room, have spent the past many years or decades trying to measure, and that's the UV luminosity function. And so what I'm showing here is a compilation of measurements from a review paper I wrote this year at redshifts 4 through 8 from the UV luminosity functions. Here are all the studies listed here where the data come from on the side. The ones in bold are kind of the more recent ones that have more of the better measurements. And you can see that we are actually, number one, in quite good agreement when you look even out to redshift 7 and 8. And number two, there's actually a function here. You can see it. You can see that it does look like the UV luminosity function out to the higher redshifts follows a Schechter function. Maybe at redshift greater than 7, it could follow other functions as well, but it at least looks consistent with the Schechter function. And so in this paper, I took all the data from all the studies in the literature and fit them simultaneously to Schechter functions, shown here, and you can see the evolution in the bottom right-hand panel. And rather than fit the individual data points at individual redshifts, I fit three functions, m star of z, phi star, and z, and alpha of z. And you can see the trends shown here. Okay? And so what this shows us is that, number one, we have a good measurement of the UV luminosity function at all redshifts. And number two, we can see how it evolves. And what's extremely interesting, and something we've known for a number of years now, is that the Feynman slope alpha, this key parameter, seems to steepen as you go from redshift 4 down to redshift 10. And so what that means is that lower luminosity galaxies, specifically the ones that we cannot even yet see, are responsible for a greater and greater fraction of the total UV luminosity density as we go towards early times in the universe. So this is sort of the state of the field about a year ago. These studies only probe to UV absolute magnitudes of about minus 17. That's sort of the limit of the Hubble ultra deep field at about redshift 5 or 6 or so. And we know that we need to go fainter for reionization. And so it was that sort of desire to understand what's happening beyond these limits was one of the many, many things that led to the advent of the Hubble Frontier Fields program. So the Hubble Frontier Fields is a director's discretionary time program that Hubble's been doing over the past 3 years, taking extremely deep imaging of 6 galaxy clusters and 6 adjacent parallel fields. The depth of these images are almost at the depth of the ultra deep field, not quite, about 29th magnitude or so. So there are a few studies that have now been taking advantage of these data. I'll talk about one that's been led by postdoc Rachel Livermore at UT Austin. And this is a paper that you can see on the archive that's under review right now, where we looked at the first year data from the Hubble Frontier Fields. There's Abell 2744 and Max 0416. You can see the circles show where our identified high redshift galaxies are. In this paper, we looked at redshift 6, 7, and 8. And the red line shows where the region of really maximum magnification is, I believe at redshift 7 in this figure. And one thing that's not apparent when you look at sort of the pretty version of these figures is that galaxy clusters are bright. Specifically, the extremely bright cluster galaxies and the intercluster light does a great job of hiding the highest magnification regions. And so soon after this data came out, it became apparent that if we kind of used our original techniques of just trying to find sources and make luminosity functions, we were going to miss some of these faintest, most highly lensed galaxies. And so there are a number of ways you can do this. You can use GalFit. You can try and use median smoothing. We tried to use a technique known as wavelet decomposition, where you take an image and you separate it into sources on different scales, and you basically subtract the bigger scale objects. That would be your intracluster light. That would be the biggest scale, even the cluster galaxies. And you leave the tiny little sources that are likely the high redshift sources we want to find. This figure here illustrates to you that when you zoom in right on this region of highest magnification, there's still a lot of light there. And so we'd like to get rid of that. And through this wavelet decomposition, now we're looking at the same regions. You can see if you get rid of those bright cluster galaxies and the intracluster light, there are all kinds of tiny little specks and dots there waiting to be identified. Of course, they're not all high redshift galaxies. We had to think about, could they be globular clusters within the galaxy cluster itself, which we don't think so, at least not. Some of them I'm sure are, just not the ones we selected as high redshift galaxies. And so there are a few other papers up here using complementary techniques, and they all seem to work pretty well. You can, in fact, successfully remove the galaxy cluster and find these really distant, faint galaxies. So that was the paper that's on the archive. Rachel, skipping ahead, has now done an updated analysis using the year 2 clusters. Get to that in a second. There we go. Here are the next 2 clusters. And over 4 clusters, as well as the 4 parallel fields now, we're up to on order 700 galaxies or so, about 430 at redshift 6. This is just from the frontier fields. This does not include the UDF or the candles fields at this point. Okay? And even about 20 or so at redshift 9 and 6 or so at redshift 10. And so when we take these and update our luminosity functions, again, this is an update from the one that's on the archive right now, you can see that we basically don't see any evidence that the luminosity function turns over. There are a wide variety of reasons that believe it should turn over at some point. This does not say it does not turn over. It just says that any turnover must be at magnitudes fainter than -14 or maybe even -13. Another interesting thing is if we look at the Feynman slopes we're deriving, they're not that crazy. We get -2.03 at redshift 6, which is pretty consistent with what I got from that sort of what I call the reference luminosity function analysis of all the data, which was -1.91 at redshift 6. And it's also consistent with the value that we'll probably hear about from Richard of -1.95 at redshift 6. And the interesting thing here is what Richard found in his recent paper is that these galaxies are incredibly tiny. They're so tiny, in fact, that you may not estimate your completeness correctly. And certainly that's something that we're going to have to look harder at. But at the very least, at the limit of our data, it doesn't appear to significantly affect our slope, and then we get right around -2. It does appear to get steeper, -2.1 at redshift 8, -2.2 at redshift 9. Of course, there's less data there, so this will get better as we use the full 3 years of the frontier fields. All right, and this is a figure we just made to illustrate. We used the Bayesian information criterion to say at what level could we rule out different turnover magnitudes. And essentially at redshift 6, there's very strong evidence against a turnover brighter than -13. So the previous assumption that we could integrate the luminosity function down to -13 is probably a pretty good one. So we can sort of kind of check this off with an ish, because of course there are some things that need working on, various biases that may be present in the analysis, and so this can certainly get better. So the second one is the conversion from UV luminosity density to ionizing photon density. We'll touch on this in a little bit, but I want to talk about the escape fraction, because this is really the dominant uncertainty. You cannot directly measure escaping ionizing photons at redshift 7. There's simply too much opacity along the line of sight. So you need to do this in the local universe, maybe out to redshift 2 or 3, where you have a chance of seeing these photons. And almost all studies are resulting in non-detections at the limit of less than 10%, less than 5%, sometimes even less than that in stacks of galaxies. There are some notable exceptions, especially in the past year or so. We've started to see some interesting systems that have escape fractions of 10%, 20%, even 50%, but they seem very rare. And so we're sort of at a point where we're trying to figure out how common are those systems and what are the physical properties allowing them to have such ionizing photon escape fractions such high. But if they are rare, we need to try and figure out how can we actually ionize the universe, reionize the universe, if the average escape fraction is quite low. And so to do this, I decided I wanted to take these reference UV luminosity functions. So we have a good idea of the luminosity function. And I want to combine them with simulations, specifically the escape fractions from simulations, and see, can we reionize the universe? And so I'm using data from a paper from Jan-Peter Pardakuper from the first billion years simulation. This is a figure from their paper. This is a 2015 paper showing the escape fraction as a function of halo mass. And so I took their data and turned it into this figure, sort of the same thing. It's the probability distribution function of the escape fraction for different halo masses. And you can see when you get to very low halo masses, 10 to the 7, 10 to the 7.5, the escape fraction is quite high. The problem is, throughout the epoch of reionization, we don't know if these galaxies are forming stars, these halos. Yeah.
Since, as I'm sure you know, different folks have, or there are at least two well-used escape fraction definitions. Which one are we?
It's absolute.
Okay.
Yeah. And if you look at the halos that we are maybe just starting to see, 10 to the 9 or so, the average escape fractions are quite low, although you'll notice there is a little peak at high escape fractions. This is due to supernovae evacuating gas, allowing a high escape fraction in some very small fraction of systems. So maybe this can explain why we're seeing high escape fractions in sort of the rarer system. But what I wanted to see was if we combine these distributions with our luminosity functions, can we actually ionize the universe? And so, of course, I don't have halo masses for my system, so I have to get that in some way. And we chose to do this through abundance matching using the process that Peter Baruzzi has created. And so here are UV luminosity functions again, and here is the halo mass UV magnitude relation if we do our abundance matching. One thing I noticed when doing this is that if we just let alpha kind of keep going, it gets quite steep, minus 2.8 at redshift 14. I don't know what to think about that. I know there are some results simulations, maybe we'll hear some from Charlotte Mason, that show alpha this steep, and so maybe that can happen, maybe not. And so we did two analyses, one where we let alpha keep evolving, and one where we stop alpha evolving at the redshift 10 value, which is minus 2.35 in this trend. And so we get a slightly different version of our halo mass UV luminosity relation. And so for the rest of what I'm going to show you, I'm going to assume this fixed alpha at redshift greater than 10 model, but we do explore both cases. So we have results for both of these. So the punchline here is it doesn't work. If we take the escape fractions from these simulations, we combine them to the luminosity functions, and we calculate the ionizing emissivity as a function of redshift. You can just kind of look at this dark blue curve. It's indicative of the uncertainties here. It never reaches the point where we can reionize the universe. And if we calculate the ionized volume filling fraction here, it's not very good. It doesn't get anywhere close by redshift 6, let alone even by redshift 4. So clearly, we cannot just take these escape fractions right out of the box. We should also look at our other assumptions. To make this figure, we assumed that you integrate down the luminosity function to a point where you're at a halo mass of 10 to the 9 after reionization and a halo mass of 10 to the 8 before reionization. Okay? Those could maybe both be fudged a little bit. We also assumed psi-ion of sort of a common value typical for maybe low but not extremely low metallicity systems of 25.34. And there's evidence that this may be evolving as well.
I appreciate the talk subsize and reionization, but looking at this figure, do you have as big a problem at redshift 4 where there's no doubt what the ionization fraction of the IgM is?
Absolutely.
There's even less doubt about what any of the galaxy parameters are.
Yes. So this does not work. Agreed.
By a lot.
By a lot, yes. So we need to change things. And so we've developed an MCMC analysis where we created a decent number, although hopefully not too many free parameters to try and probe the parameter space. Let's take everything that we don't know and just let it be somewhat free and see what comes out. Okay. And so the first thing we did is, what if these escape fractions are just too low? Okay, from the simulation. What if there's some numerical effect, I don't know, that's just keeping them all too low? And so we applied a scale factor where you can take the escape fraction from the simulations and scale them up or down if you want to. But we keep the halo mass relation. So the escape fraction as a function of halo mass stays the same, but the whole thing gets scaled up or down. Likewise, we allowed the minimum halo mass for star formation before reionization to vary. There's some evidence from simulations by Xu and Wise and Norman that maybe before reionization you form stars and halos even all the way down to 10 to the 3. And we're not talking about population 3 stars, but maybe metal-enriched stars. Thirdly, we allow the ionizing photon production efficiency to evolve both with redshift and with magnitude. And those values in parentheses are just showing the allowable parameter ranges. And maybe more interestingly, we allow for the possibility of AGN. As X alluded to, at redshift 4, we did a very poor job, but certainly AGN are there at redshift 4 and are contributing to the ionizing background at redshift 4. This was motivated by recent work by Gialongo and then a follow-up paper by Maddow and Hart saying if you had sort of a provocative AGN ionizing emissivity with redshift, this purple line here, you actually could reionize the universe completely with AGN. This was quite different than sort of the older model by Hawkins et al. 2007. And so essentially what we did is we adopted this whole possible range of parameter space, and the AGN emissivity is allowed to be free within this range. So we allow the slope to vary, We also have a cutoff redshift where beyond a certain redshift you don't allow AGN. That can vary as well. And then the whole thing is actually allowed to be scaled down as well. That scale is really like an escape fraction for AGN. Okay, these values here assume that all ionizing photons escape. Certainly true for quasars, maybe not for lower luminosity AGN. So those are our free parameters. We need to have some constraints as well. The Lyman alpha forest emissivity at redshift 4 and 4.75. Those are very well measured, so we know how many ionizing photons are out there at redshift 4. We need to match that. We also have a decent idea of what the ionized fraction of the IgM is, closer to redshift 6. And so we use the model independent constraints of the recent paper from McGreer of greater than 0.91 at 5.6 and 0.89 at redshift 5.9. And finally, we use tau from Planck. We use the 2015 value, but we also have done a run with the 2016 value as well, the lower 2016 value. And so the punchline is if we allow all these parameters to be free, these are the posteriors that we derive from our simulation. And there's a lot to take in here, and we don't have a lot of time, so I'll just highlight a few things. Okay. First of all, we do need some AGNs, it looks like, okay, if we allow them to be in our parameterization. Specifically, this is sort of the range of AGN that we would need, of AGN emissivity. And sort of intriguingly, this follows, this dashed line is what happens if you just blindly fit the data that was here in the plot from Piero's paper. So you need some amount of AGN, okay? We also need some evolution in the ionizing photon production efficiency, which I'll show you in a minute. We also need the escape fractions to be about 2.5 times larger than that from the simulation. Okay, but as I'll show you in a second, if all these can happen, you actually can reionize the universe with relatively low escape fractions. And that's essentially what you should take away from this talk. And we'll come back to that. And so here's maybe the more interesting plot. The figure on the upper left shows the ionized volume filling fraction as a function of redshift. The red line is the line from Brandt's recent paper. And you can see that it satisfies our two constraints here, but our analysis gives you a more extended reionization history towards higher redshift. And that's really driven by that very steep UV luminosity function at high redshift. One thing I want to point out here is, I don't know if we'll have any talks on it at this meeting, there's a lot of results from measurements of Lyman alpha emission from galaxies that hint that maybe the universe is somewhat highly ionized at redshift 7, or sorry, highly neutral at redshift 7, 20%, maybe even 50%. And so that is not a constraint in this model. If it was, it would push this down right about here by quite a bit. We elected not to use it because there's a lot of uncertainty. The samples are small. There are theoretical papers coming out on both sides of the issue almost monthly, at the very least, saying you can have the suppression of Lyman alpha with almost no neutral fraction, or maybe you need a very large neutral fraction. So that's something to keep in mind. We can match the Planck tau fairly well, and we can also match the ionizing emissivity. What this shows here, blue is the total emissivity, purple is from galaxies, red is from AGN. Okay, and so a couple quantities to look at. We can reionize the universe by redshift 6, okay, which is good. And the average escape fraction at redshift 7 is only a few percent. It does need to be somewhat higher in the past, although the bulk of the ionizing photons are happening at redshift less than 10. You only need escape fractions of a few percent, and you can actually get it done. And so coming back to the Lyman continuum photon production efficiency, these lines here are what come out of our simulation. And so from bottom to top, you have redshift 4, 6, 8, 10, 12, and 14. And you can see it goes up with redshift, and we also allow some amount of magnitude evolution to a point. We don't allow it to go higher than 26 because there's no observations or models which are putting it at higher than 26. So that's an assumption that we made. But what's intriguing is at least at the very narrow range where we overlap with observations, okay, the color coding is similar between the points and the redshifts. It actually works pretty well. We match at redshift 4, we match at redshift 8, and even the fainter point from some work by Dan Stark at redshift 7 and change appears to match pretty well. Okay, those were not constraints on the model. So it's pretty exciting to me that it happens to match. Okay. So of course, that was a lot of free parameters. You may wonder, are they actually all needed? And so we ran more runs than I can even remember, but here's sort of a master table showing you essentially a goodness of fit quality. It's this Bayesian information criterion again. So low numbers are good, but really it's the difference between a given value and another value. If the difference is greater than 6, the lower value is a preferred model. If it's greater than 10, it's very strongly preferred. Okay, and so in green, I'm sort of showing you the models that kind of work. So the top one that I called all, it was allowing all the parameters to be free. There are a bunch of ones where we try and turn off AGN. We don't allow anything except the escape fraction. We only allow AGN at redshift less than 6. They don't seem to work. A couple other models sort of work if we don't allow any evolution in psi ion, or if we don't allow any magnitude evolution in psi ion. These also seem to work equally well. Although I took a look at these, And these require AGNs to really dominate the emissivity all the way out to redshift 8, whereas the fiducial model only requires them to dominate at redshift less than 6. And so possible, but maybe not likely. And so the conclusion to take away from this analysis, the key one for me is that you can reionize the universe with mean escape fractions of about 4 to 5%, which is much lower than previously thought, and almost in line with at least some of the non-detections from the literature. And the main difference here is, if you look here, I didn't touch on this plot, this is showing you the limiting UV magnitude as a function of redshift. This is driven by the evolving halo mass as well as the evolving neutral fraction in the IgM. It's below minus 13 at almost all points. And so we go fainter, and we allow evolution in the Lyman continuum photon production efficiency. That gives you a lot more ionizing photons, so you need a lower escape fraction. It appears that quasars or faint AGN are likely required at redshift 4 to 6, and maybe even quite important all the way out to redshift 6. And that's similar with a lot of recent observations that we've seen, that there are large fluctuations in the ionizing background at redshift 5 to 6, that maybe helium-2 is reionized at slightly higher redshift than previously thought. And so this is, of course, by no means conclusive. It's just consistent with our model. But it's something that we need to get a lot more observations of. And again, there's likely some evolution required in psi-ion. So I just wanted to steal 1 minute from my questions to touch on another issue. We're going to have a talk in a little bit from Richard on the evolution of the stellar mass to halo mass relation. So I just wanted to give a brief advertisement of some work we've done here. And just the primer is, we had hints from Peter in 2013 that galaxies at fixed halo mass had a higher stellar mass to halo mass ratio at higher redshift. This was sort of unexpected and implies that something is happening at higher redshift, higher star formation efficiency, who knows, that's driving this. And so we made a first attempt just last year using UV luminosity functions, doing abundance matching to again measure this quantity. And we were looking at fixed stellar mass, so stellar mass of about 9.8 in log, corresponds to about L-star galaxies at redshift 4 through 7. And essentially we saw the same thing, that the stellar mass to halo mass ratio, or what we called the stellar baryon fraction, the fraction of stellar mass to the fraction of baryons in these halos, was rising with increasing redshift. And there are a lot of reasons why this analysis had problems, of course, and the biggest one is you're using UV luminosity functions, and there's a lot of scatter. And we tried to account for that, but maybe we underestimated the scatter. But what was intriguing was this aligned with recent clustering results from Harikane and Uchi et al., who did actual galaxy clustering out to redshift 7 and found a similar result, measuring the halo mass through clustering. We'd like to do better, and so we've been doing this again with stellar mass functions. This is work by my now former PhD student, Mimi Song. She defended last Monday and started her postdoc 3 hours ago at Goddard, which is why she's not here, but maybe next year she can be here to tell you about this work. She's been working on the stellar mass to halo mass relation, taking her stellar mass functions and using abundance matching to trace this relation to higher redshift, and gets a very similar result. And so we'll hear a different result in a little bit from Richard, and I think it's intriguing whichever way we go, and so certainly there's a lot of work to be done here to figure out what's going on in the distant universe. Thank you.
Great. Questions for Stephen? If you have a loud voice, I guess you can shout. If you don't, wait for me. Andrew?
I didn't quite pick up what's actually in your likelihood function.
You're not loud enough.
I didn't quite pick up what's actually in your likelihood function, and I wonder if you could also comment on why you choose to use the information criteria rather than a straightforward model selection approach.
It's a good question because it's what we knew. It seemed to be a good quantity that took into account not only the goodness of fit, but also the number of free parameters and the number of constraints. But I'm happy if you have a suggestion for something else we can look into. That would be great. As far as you're referring to the constraints, or which specific aspect of the likelihood function?
Well, I guess what actually goes into it. I wasn't actually totally clear what data is in the likelihood function.
Got it. So that's go back to this plot here. We're getting there. So essentially we have three overall constraints. It's the ionizing emissivity from the Lyman alpha forest. It's the neutral fraction in the IgM at redshift 5.6 and 5.9 from observations of quasars, and it's the Planck tau. And so there's essentially three constraints. Some of them have 2 values, some of them have 3 values, some of them only have 1 value. And so those are the things that are contributing to the goodness of fit.
Next question.
Hi. So I was just wondering what the spread in the escape fractions that you got were, because Europe Matthew had a paper earlier this year where they found like 4% of their galaxies had very, very high escape fractions at like redshift 2. So if you had things like that within your model and how much they contributed.
Yeah, it's a great question. So there's a plot I took out for time that was not enough, because I still went over. And so this figure, and maybe this is not answering your question, let me know. This is showing the average escape fraction as a function of redshift. This is actually before I apply any scale factors. And it shows something like 2%. And so I was sort of quoting average numbers throughout. But that's not quite indicative of what's actually going on, because most of the halos we're seeing are the ones that had very low typical escape fractions and then that little blip at high escape fraction. And so if you look at the actual escape fraction values for a population, what you see is, I just looked at this number, I think it was 7% of galaxies have escape fractions over a few percent, and the rest do not. And so maybe that's consistent with sort of a small fraction, but not insignificant, having higher escape fractions, whereas the bulk have very low escape fractions.
I'm reminded to ask you to come down and set up, please. Another question? Oh, Eric, you're loud enough.
Okay, so I have a couple like totally dumb questions. So what does minus 12 mean in terms of star formation rate?
Oh, very, very small.
Yeah, I know, but
Yeah.
like how little is one?
I don't know off the top of my head.
Okay.
Somebody in the room probably does, though.
It would be 15 divided by 1,000.
Okay, 15,000. Okay, cool. And then for the AGN, because you have this, you say you need a big AGN contribution. Like, how big is big? Should I be worried about it? Do you overproduce the amount of mass in black holes that we expect to be in place by redshift 4 or 6?
That's a good question. I haven't looked into that. That's something we should look into. What I know is that there seems to be increasing evidence from complementary methods looking at the IGM that there's probably a larger contribution from rarer sources like quasars than we think now. And so it seems as if they're allowed, but I haven't looked at that specific quantity.
Maybe one more while Charlotte
Well,
sets
it's not
up.
a big deal. What would happen to the entire analysis if AGN didn't contribute much at redshift greater than 5?
Yeah, so we ran that, and we ran it at redshift greater than 6. I can't find it. I don't have the plot here. I can show you later. It essentially produces worse results. And so the biggest thing you don't get is you really aren't quite getting enough ionizing photons at right around redshift 6, right around that key point. And so you reionize too late. If you don't allow AGNs at all, you don't get anywhere near the number you need even at redshift 4. So you certainly need them at redshift 4.
Yeah.
So the implication is that you need a much larger escape fraction.
You could, yes, but if you, right.
What other out is there?
So here's the key thing is, and you could certainly parameterize this escape fraction scale factor was not redshift dependent. And so if you give yourself a larger escape fraction at redshift 5 and 6, then you have to give yourself a larger escape fraction too early on, and then tau is too high. So certainly you can make that a function of redshift and add another free parameter and maybe solve that problem. So in the meeting a couple weeks ago in Malta, I showed a similar result and said at redshift 6, if you cut off AGN at redshift 6, you could do about as well, but that was letting psi ion get arbitrarily high, and it was sort of getting crazy high at high redshift. And so if you cap that at 26, then you do need AGN at redshift 6. But admittedly, there's a lot of free parameters.
Great, let's thank Stephen again.